As you can see, this bridge was exceptionally long and narrow, over half a mile long, only 39 feet wide. It lasted just 4 months. During construction, we see the steel girders, 8 feet tall, which were supposed to stiffen the bridge against bending. However, some up and down vibration was observed during the entire useful life of the bridge. Here's opening day. On November 7th, the bridge suddenly went into a twisting motion. The wind speed was a steady 42 miles per hour. This was enough to keep the bridge oscillating in one of its natural modes of vibration with a period of 5 seconds. A professor of engineering went out to see what had happened. He's coming back, walking with some difficulty, along the nodal line, which is the center stripe of the roadway. It's remarkable that the girders were this flexible. This is photographed at normal speed. However, a collapse was inevitable after a little more than an hour of this. The car had been abandoned earlier. No one was injured in the whole affair. However, a small dog in the car was frightened and was afraid to come out, and he perished along with the bridge. The bridge was rebuilt using a stiffening truss instead of girders. The new bridge is completely stable.
Hello everyone, this is the fifth lecture of Vibrations and Waves. In the previous lecture we've been looking at driven steady-state solutions, and we've seen that there are no two adjustable constants in that case. So if you have a spring, it doesn't matter what initial position or velocity the object has. As you're driving it, you wait enough time, you would have the steady-state solution regardless to the initial conditions. Today we would be focusing on the transient solution, so this initial stage. So let's start with the spring. We have a spring with mass m and constant k. Omega 0 squared is K over M. We have damping in the system, so gamma equals V over M. And let's first look at the solution that we had for the undriven case. So the undriven looked like this. X equals some constant B. There's an exponential decay due to damping, so e to the power minus gamma over 2 times t cosine omega 1t plus beta. Omega 1 is square root of omega 0 squared minus gamma squared divided by 4. The driven solution is given by following: A cosine omega t minus delta. And as I said, in the case of the forced oscillations, the driven solution, A and delta are defined in the system. So A is given by, let's say, in terms of the force, F over M, divided by square root of omega squared minus omega 0 squared, the other way around, omega 0 squared minus omega squared, all squared, plus gamma omega squared. And the tangent of delta is given and that is omega gamma over omega 0 squared minus omega squared. Alright, we've seen this in the previous lecture. Now, let's go one step back and look into the differential equations that these solutions satisfy. The differential equation for the undriven case, that is x double dot plus gamma x dot plus x plus omega 0 squared equals 0. And for the driven case, we have something similar initially. Then on the other side, we have the driving force or the displacement, as we've seen last time with the pendulum. So we can write F0 over M times cosine omega t, or you could write it, this is if you talk about force. If you want the displacement, you can write eta 0. Let's put it up here. Eta 0 omega 0 squared cosine omega t. This is displacement. Right? Okay. So we have two solutions here. The first one, note that it satisfies the first equation here, and the second one satisfies the second equation. Note that omega here is that's my omega, is the driving force or displacement omega. Right, so it's the same one as here. If I wait enough time, I will get that omega. If I just let the system start at the beginning by itself, then it wants to oscillate with this omega, with omega 1, and decay. So what happens if we add these two solutions together in order to try and derive a general solution? Well, let's see if this equation is satisfied if we add the undriven solution into this equation. Notice that this equation is still satisfied if we add them together, because the undriven solution, we know it satisfies this differential equation and it gives 0. So basically, if I add 0 here to this solution, then this solution would satisfy the right hand side here. So we add both solutions together, we substitute in the driven case, this has to be satisfied. And we do that. Why do we do that? Then we should get something in return, and that is the two adjustable constants that we want, and that will give us the description of the transient solution. Okay, so the solution now we can just write it down, the general solution. The general solution would be this plus this. X equals A cosine omega t minus delta plus B e minus gamma over 2 times t cosine omega 1t plus beta. This is the steady state. You wait enough time, the system would be oscillating with my frequency. And this is the transient. The system would be decaying by a factor of E if you wait a time of 2 over gamma. Alright, so let's look what happens at time t equals 0. So at time t equals 0, let's say that x is x0, the location, and the x dot is the velocity t0. So these are the initial conditions now. Let's make a drawing. I'll first make a drawing for the steady case. So this would be this is time, right, and this is the amplitude. The steady case has an amplitude of A. I'll do it here. Right. And it goes like that forever. This is only the steady solution. Now we have another frequency. So this would give me the period. This will give me the period. Let's write it here. If I'm looking at here. So this is the period t, which is 2 pi over omega. It's my omega. Now, let's look at the decaying case. First, I'm going to make some decaying curves to help me with the drawing. Now, we will have a different frequency. Doesn't have to be the same frequency, right? It can be larger or smaller. This is for the decaying case. We have something like this. Oops. In a similar way here we can put, this is T1, which is 2 pi over omega 1. Okay. Now there's a question, what would you see if the driving frequency was very close to omega 1? Let's put this back. This is the driving frequency, and this is omega 1 of the system. What do you think would happen if I drive the system with omega, which is very close to omega 1? Not omega 1, but very close to omega 1. What you should see then is a Beats effect, right? Because look at this. What do we have here is a superposition of two oscillators, superposition of two waves, and we see that we have two frequencies here. So if you remember, you're going to get omega minus omega 1, one term, divide by 2, and that would give us the envelope of the beats. Alright, so we're driving the system, we're putting some energy into the system. So we apply some work dW equals the force, the dot product, dx. This is the work. And we are interested in the power, how much joules we put in the system per second. So dW dt. This is the power. So that is F dot B. It's a 1D problem. The force can be in one direction, and the velocity is in the same direction, so we can just drop the vectors and the dot product. So we have F times V. And if you want to find V, you go to the solution, to the steady state solution, and we want to find out the power after we waited enough time. So we have, let's put it here. You see that? Yeah. So X dot is minus omega A sine omega t minus delta. So now we can write for the power, that's for the power P. So P equals F times V, and V is X dot. So it's a minus f0 omega a cosine omega t times sine omega t minus delta. Right, x dot is minus omega a sine omega t minus delta, and the force is f0 cosine omega t. So this is the power. Now what do we do with this? We can rewrite the sign here. So we write minus f0 omega a cosine omega t times, I can write this as sine omega t cosine delta minus cosine omega t sine delta. This would be proper brackets. Alright, so this is what we have. Now note, we're not interested in the power in every single moment, but we want to know the power after few oscillations, okay? 10 oscillations, 100 oscillations, how much power we put on average in the system. So for that now, we can take the average here, and if you take the average in time, we note the following. This is sine omega t times the cosine on one hand, and there is a cosine omega t times the cosine omega t, so cosine omega t squared. The average for the first is 0, and the average of the second is 1/2. So this gives 1/2. Okay, so now if we put things together, we can write here P average if you want. This is our average. That would be now, it's a minus, with a minus there would be a plus. There's a factor 1/2 here. If I take it out, so f0 over 2 omega a and sine delta. Okay, so now we know the average power in the system. Okay. Do we know delta? We want to find sine delta. We know tangent delta, right? Here. See that? We know tangent delta, and we want to know sine delta, and that is easy to find. Right? This is delta. This is omega gamma. This is omega 0 squared minus omega squared. Now we know the tangent, right? Tangent delta is omega gamma over omega 0 squared minus omega. So using Pythagoras now, you can write sine delta that is this, divided by this, so it's gamma omega, divided by, using Pythagoras now, square root of omega 0 squared minus omega squared plus gamma omega squared. You see this there? Yeah. Alright, so we can substitute sine delta into here, and if you look up the A, there's a term in A, where's A? Here's A, which is exactly this square root that we have here with the sine delta. So that cancels out. Have this up here. This cancels out. And we can finally write P, the average power, as F0 squared divided by 2m omega squared gamma over omega squared minus omega 0 squared minus omega squared, all squared, plus omega gamma squared. If you divide everything by omega squared, we end up with F0 squared gamma divided by 2m. And here we have omega 0 squared over omega minus omega squared plus gamma squared. Just another way of writing it. Alright, now without really looking at this equation, as always, we want to see if we are able to intuitively predict things, and then see if the derived relation for the power is satisfying those predictions. So let's ask ourselves, what happens, for example, if the in terms of the power, what happens if the mass is very large, is infinitely large? What would you expect that the power should be, without looking into the equation? So think about it. If the mass is so large, right, you can't even move it because it's so large. So you would expect that there would be no power in the system. Nothing is actually going, right? Now what happens if, so let's write that down and then we get a check. So this is our prediction. If m goes to infinity, then p goes to 0. What if the force is very small? The driving force is very small. Well, same thing, you would say, well, if the force is very small, it tends to 0, F tends to 0, then there would be no energy in the system, and then there would be no, you're not applying any work, so there would be no work per unit time, there would be no power. Okay, so P would have to be 0. You could have done this also before even deriving the relation here. What happens if the resistive forces are so large? They are infinitely large, so gamma is tending to infinity. Same thing, if the resistive forces are very large, then you would expect that nothing's moving. If nothing is moving, there's no power in the system. You're not putting any power in the system. So P would be 0. And we're talking about the, I put P here, but let's also fix this. This is the average power, just to make things more precise. What happens if the driving frequency is very small, so it tends to 0? You would say it would the object would never pick the velocity, right? So there would be no velocity, so there would be no power, right? So right, if omega goes to 0, then P also goes to 0. What happens if the frequency, the driving frequency is very large, so it goes to infinity? As we've seen last time, nothing will be moving, right? It's just too fast. So there will be no power as well. Alright, and the last one I'll put here. That is what happens if the frequency, the driving frequency is tending to the natural frequency. So the frequency is tending to omega goes to omega 0. Now, you may think then the power would be at its maximum level, and that is true. So P would tend to some P max. Now let's look at the equations and see if these are all satisfied. When m goes to infinity, there is no power. That is 0. When f0 is 0, P is 0. When gamma goes to infinity, P is 0. When omega goes to infinity, where do we see that? When omega goes to infinity, yes, you take the limit. Omega goes to 0. Yeah, when omega goes to 0, it goes to 0 here. So the power is 0, right? This is 0, this is 0, this is a number here, and this is 0. When omega tends to infinity, now where do we see that? Yeah, here. If omega tends to infinity, this is 0, this is infinity. The whole thing goes to 0. And finally, when omega goes to omega 0, if you make the substitution, so this would be 0, this would be omega 0 squared, omega 0 squared, it would cancel out, right? And we end up with f0 squared gamma over 2l. We have it here actually. Yeah. Okay, so in this case, we have P max f0 squared over 2 m gamma. We lose one gamma here. Yeah. Okay. Is that correct? if omega goes to omega 0, this would be omega 0 minus omega 0, this would be 0. We have omega squared here, we lose 1 omega with this one, we end up with f0 squared divided by 2m gamma. f0 squared divided by 2m gamma. Okay, that's fine. Now we draw, sketch for the power. It looks something like this. Quite symmetric. This is the point of P max. This is a point, this is an interesting point, which is half P max. At half P max, if gamma is much smaller than 1, the peak becomes very narrow, and this point here and here, we'd have omega 0 minus gamma over 2 and omega 0 plus gamma over 2. So at exactly half P max, this length here would be gamma. If gamma is very small. There's a figure on page 99 of French. So figure 412. It's quite important to understand this figure. So I suggest you to look at this figure. There's two parts, A and B. In the first part, they describe the. It's a very similar figure, but with the quality factor. You see, the higher the quality factor, the narrower this becomes, and the higher the peak goes. All right. Let's just let's prove this. Let's show that at half P max, if gamma is very small, then indeed the width here would actually be gamma. It's quite easy to. This will be the last thing we do today. Do it here. Yeah, let's do it here. Actually, I want to do it on this side. Okay, let's see what we need. We need P max, and we need P. So we can leave this part. Okay, this is P. And this is P max. Now, what happens at half P max? It's right in here. So half P max, that is half f0 squared over 2m gamma. That's half P max. Equals to, now I'm substituting here, that is f0 squared gamma over 2m. times times 1 over omega 0 squared over omega minus omega all squared plus gamma squared. These cancel. This cancels out. We have on one side we can write 2 gamma squared, and on the other side we can write omega 0 squared over omega minus omega all squared plus gamma squared. So we have gamma squared equals omega 0 squared over omega minus omega all squared. Almost there. So gamma is we know gamma is positive. Gamma is omega 0 squared over omega minus omega. Now if you multiply by omega and then move this to the other side, you have omega squared plus gamma omega minus omega 0 squared equals 0. To solve this equation now, what do we have? Omega equals plus or minus omega equals minus gamma plus or minus square root of gamma squared minus 4 omega 0 squared. Now note as the minus, so that's a plus, and all divided by 2. Right, we're almost there. Now we make use of the assumption that gamma is very small, is much smaller than 1. Gamma is much smaller than 1. So omega equals minus gamma over 2 plus or minus the square root of 4 omega 0 squared, that is 2 omega 0, divided by 2 is just omega 0. Okay, so omega is either at omega 0 minus gamma over 2 or omega 0 at plus gamma over 2. Okay, so and if you take the difference, of course, and it's obvious that, so if I write omega 1 and omega 2 here, so omega 1 minus omega 2, that is exactly gamma. That is the difference here. Alright, that's it for today's lecture.